Okay, good evening. Tonight's lesson is over um, arc circumference or arc length, I'm sorry. We've been talking about arc measure so far in this chapter quite extensively. So you can see here I've got arc AC. Arc AC can be large, have a large measure, which we measure in degrees. If I make the arc as large as can be, it would be 360 degrees. If I had halfway around the circle, it would be 180 degrees. So we're used to arc measure. Well, we're going to add to this today arc length. Certainly, this arc has a length. I could walk this length. I could measure the length of that arc, and that's what we want to do today. Looking at that arc in its length, we can see that the length of this arc is going to have something to do with the measure. But what else? Not just the measure, but also the size of the circle, right? Because I could have 180 degrees and have a large circle or a small circle. So it's not simply the measure. That's not enough. We need to also look at the size of the circle. So that's why the circumference of the circle is going to be important. So looking at calculating arc length, here I've got the measure of this particular circle, or this particular arc, is 118 degrees. You can see how that can be adjusted. What is the length of this? Well, I want you to think about this important ratio here. This ratio is found by taking the measure of the arc, which is 110, and dividing it by 360. Excuse me. What have I found when I divide those? Well, I get 0.31 in this case. Now, the units here are a little bit messed up. It's not degrees. You can think about this as the percent. This is the percent of the circle. Percent of the circle covered by the arc. In this case, 31% of the circle is covered by the arc. I could expand that to, if 180 degrees was going to give us what, 50, right? 50% of the arc covers the circle. I could take it to 75%, right there, 75%. Or I could take it to 90, or 25%. 25%. Hey, that's 90 degrees. We would expect that, right? So what I'm finding is the percent of the circle, and now we can just put these two things together. If I want to know the arc length, what I'm going to do is I'm going to take the measure of the arc. I'm going to take the measure of the arc divided by 360, and I'm going to get that percentage of the circle that I'm talking about. And then I'm going to multiply it by the circumference. I'm going to multiply it by the circumference of the circle. So I could say that this way too. I'm going to take the measure of the arc, measure the arc over 360, multiplied by 2 pi r, because that is how we calculate circumference. We should also realize that the central angle has the same measure as the arc. Therefore, we could also write it this way: central angle divided by 360 multiplied by 2 pi r. That would work as well. Okay? So looking at this example here, I have got a circumference. This circle has a circumference of 23.25, and it is 26% of the circle. So I should be able to, I'm going to calculate, I should be able to take this and take that that percentage and multiply it by this circumference and get the distance of the arc, 6.05. Again, these units should be ignored. Geometry Sketchpad doesn't know what it's talking about with those units. So 6.05, I'm going to check that with my length, which already is calculated. And I get 6.05. So that's correct. All right. So this is the rule that you need to own from this section. That's the rule right there. Okay, let's go solve problems with it now. That's the only rule for this section. Okay, the only rule for tonight is this one right here. So let's put it to some examples here. Again, I've already shown you the figure, so it's kind of let the cat out of the bag. But looking at example 1, a 25-degree angle is inscribed in a circle that has a radius of 5 feet. What is the length of the intercepted arc? We're struggling, I notice, we're struggling with being able to take a paragraph and draw the figure. Okay, so here's an example again. A 25-degree angle is inscribed. So picture an inscribed angle, and the radius of the circle is 5 feet. Okay, so try to picture that figure, and that figure is going to look like this. So there's my inscribed angle of 25 degrees and my radius of 5 feet. Okay, so to calculate the arc length, that's what I wish to do. The arc length, and the arc length that I'm referring to here is this red one. That arc length right there is going to equal the measure of the arc. So I need the arc measure divided by 360. Then I'll multiply it by the circumference, 2 pi r. Well, let's use some of our facts from the section, from this chapter. If this is 25 degrees, that makes this 50 degrees, right? That arc measure is 50 degrees. It is twice that amount. So my arc length equals 50 divided by 360. That's the percentage of the circle that the arc takes up. I'm going to multiply it by 2 times pi times 5, because that is my radius. And now let's simplify. 50 over 360. Multiply this by 10 pi. That's multiplying across here. We have 500 over 360 pi. I'm going to cancel out a 0. I have 50 over 36 pi. Right? It is appropriate to leave our answers in exact form, so we can just reduce this. What number is going to these values here? This would be 25, 25 18s, 25 18s pi is my unit. Leave it in terms of pi. That's the best. Okay. All right. Let's take a look now at a more challenging problem. Okay. Oh my. Clear some things off here. There we go. Clear my figure for right now. And just look at this picture here. This is an engine showing the belt on an engine as the engine drives pulleys, and the belt turns other pulleys. A lot of mechanical engines and machinery use belts like this. So maybe your folks are tearing apart your lawnmower right now to get it ready for springtime. Its blades are run by belts that are connected to pulleys, and the engine turns pulleys. And the whole point here is really we have is a lot of circles and a lot of tangents and a lot of arcs. So looking at my figure here, I have made a simplistic pulley system. You can see here that I've got a large pulley, and it's driving a smaller pulley. Your bicycle is really this as well. I'm looking for my, there we go. So here's really how the pulleys work. So here's as an example, as the large pulley turns, it turns the smaller pulley, and this smaller pulley is actually, I'm going to try to catch it. Got it. This smaller pulley is actually going to be moving a little bit faster than the larger pulley because of the mechanics of the whole thing. You'd study this type of thing in physics. You also have some torque going on here. When you ride your bicycle, you're turning a big pulley, which is turning a smaller sprocket on your back wheel, which means it goes faster than what you're pedaling. Anyway, all of this to say the chain on your bicycle is really this situation here. It is a couple tangents. This is a tangent, external tangent. That's an external tangent. This is an arc, and this is an arc, right? All of those are pieces that we're learning in this chapter and we're able to understand. So my large pulley has a radius of 9 inches, and the small pulley has a radius of 4 inches, and the pulleys are 13 inches apart. All right? So I'm given this radius here is 9, this radius here is 4, and these are 13 units apart. What we want to know is the distance of the belt. We need to find this distance, this arc distance, the other tangent, which are going to be the same, and this final arc, right? Okay, well, we're going to use our common tangent auxiliaries. Okay, we've done that a lot to construct the following right triangle. Let's piece in now and put in our values. We said that this entire distance was 9 and this distance was 4. So if this is drawn parallel, this line here is parallel with my tangent, this is going to be 4, leaving me with 5 there. This isn't quite to scale, as you can see. My pulley centers are 13 units apart, so that makes this 13. And this is, since we understand that a tangent to the radius is perpendicular, that means this is a rectangle right here. So this is just our common tangent problem. We've worked it in class. I've worked it on a video. You've worked it on homework. Now that gives us a right triangle here, and this is a 5, 12, 13 triangle. Hope you saw that. So I'm almost that I just found that my tangent, my common tangent portion of the belt are 12 inches long. Now it's left for me just to find the arc lengths. Okay, so now let's try to find the arc lengths. In order to find the arc length, I need to find the measure of this arc, don't I? I need to find the measure of this arc. All right, let's find the measure of that arc. How could I find the measure of that arc? I could find the measure of that arc by looking at this central angle. So I'm going to include a few more auxiliaries, the same common tangent auxiliaries. I'm going to take that out there. Okay. Basically, I reproduced the common tangent procedure underneath here. I'm going to take this 13 out so that doesn't confuse us. And I'm going to look at these triangles that we've created. This triangle here is a right triangle that we completely understand. It's a 5, 12, 13. This one also is the same right triangle, 5, 12, 13. It would sure be nice to know what this angle was, because if I knew that angle, I'll know this angle, and if I know those angles, I'll know my central angle, and that's the angle that I'm really after. So if I've got a right triangle, 5, 12, 13, how do I solve for that angle? I hope you're saying sine, cosine, and tangent, and that's exactly right. Let's bring our sine, cosine, and tangent back into view here. I want to find this angle, so I could do sine of that angle, we'll call it theta, sine of that angle, SOHCAHTOA, remember, SOHCAHTOA, so it's opposite over hypotenuse, So opposite of that angle is 12 over the hypotenuse is 13. Alright? That means theta equals the inverse sine of 12 over 13. So we'll pull out our calculators and we'll do the inverse sine of 12/13. And I get for a degree measure 67.4 degrees. 67.4 degrees. So we've just found this theta. That makes this one 67.4 degrees as well. If I multiply those by 2, I have now found that this angle here is 134.7. And I want to know this one. So I'm going to take that and subtract that from 360. So I'm going to take 360 and I'm going to subtract 134.76 to get 225. This angle here is 225.24 degrees, which means my arc measure is 225.24 degrees as well. And now I can find my arc length. Arc length is going to equal 225.24 divided by 360. There's the percentage of the circle that large arc takes up. We're going to now multiply that by the circumference. 2 times pi times the radius of this, which was 9. Okay, so let's take 225.24 divided by 360. Multiply that by 2 and multiply that by 9 again. And we get 11.262 pi. That is approximately, I'm going to multiply that by pi just so it's easier to understand than 35.38 inches than it is 11 pi. Okay. All right. So now we've found three parts of this belt. Now it is left for us to find this final part right here, the length of that one, and we're going to do the same thing, right? It's going to be the same procedure. So to give myself some space here, I'll take this out and we'll reduplicate that. If this is 67.4 and this is a right angle, we can find that one because they have to add up to 180, right? So this is going to be 22.6 degrees. That one right there is 22.6 degrees. How did I get that? I took the 67.4 plus the 90, subtracted that sum from 180 to find that small angle there. Now, I'm going to double that angle because what do I want? I want to find this angle measure here. Well, this is 90 degrees. This is 22.6, and this one right there is 22.6 as well, because those are congruent triangles. So now I have 180, that's 90 and 90, plus 22.6 twice. All of that comes out to be, voila, 22.2, the same value, or 225.24, same value we got over there. So this is this angle here is 225.2 degrees. Take that difference from 360 and we get 134.8 degrees. All right, 134.8 degrees. Now we're well on our way to find our arc length. Our arc length is going to be 134.8 because that's the arc measure. Divide that by 360. That's the percentage of the circle that it takes up. Multiply that by the circumference, 2 pi times the radius of 4, and we're on our way. Divide that by 360, and multiply that by 8. So I've got approximately approximately 3. Let me erase that. This comes out to be approximately 3 pi. 134.8 divided by 360, multiply that by 2 times 4 is approximately 3. Multiply that by pi, and this is going to be approximately 9.4 inches. So, the belt that the manufacturer needs to make to fit a pulley of 9 inches and a pulley of 4 inches, which are 13 inches away from each other, from center, is going to be this. Sum them all up. 12 plus 9.4 plus 12 plus 35.38. So 35.38 plus 12 plus 9.4 plus 12 again is 68.78 inches. And that's what the manufacturer needs to make. And if the belt is too large, okay, then the pulleys will squeal and squeak and slip. And if it is too tight, then it will be a hard work for your motor to turn the pulleys, because there will be a lot of friction, and that's not good. It's hard on your motor. So it is important that it is exactly the right length, and manufacturers calculate these things, and it's really high school geometry. Okay, now that was a heavy problem. You're not going to be doing lots of those, but you are going to be doing some. So I wanted to show you an easy problem in example 1, and then a challenging problem in example 2. Okay, so review whatever parts of this you need to review. And with that, I'm going to sign off, and we'll talk more in class. Good night.